it. That's small. That's all.
Okay, we're gonna start, and we don't have time to answer homework questions, so I'll answer those after class because we're behind. So homework 9 is due today. Oh, and by the way, I have to be somewhere at from 6 to 8, but I'll be on campus. I'm doing the PEP for high schools, so you can find me in the first floor of Building 9 if you're looking to submit your homework. So homework 9 is due today, and we're going to have a quiz on that topic, first order circuits on chapter 7 on Wednesday. And then our test, and the following Monday will be the first part of chapter 8. And our test is Wednesday, April 26th. I want to get it that time because April 27th is the last day to drop. So people who are thinking about dropping, I am hoping to finish grading by April 27th. And also students who missed any of the STEM speaker bonus points, remember you can go up to 4 if you're missing 4 sessions. Oh, you have less than 4 sessions or you didn't attend any, you can still earn extra credit by submitting a report on any STEM speaker. I think I sent an email over the spring break with details on what to write on your report. Okay? So, as promised, we're going to start. This is something that I wanted to start it last time, chapter 8, because it's the topic that takes a little bit of time to sink in. And I think I asked you to read ahead on chapter 8, right? Yes, I did. Whether you did it or not. Oops, what do I need to do, Cody? See, I forgot what I need to do. I need to share my desktop, huh? I didn't do that. So, share my desktop. How many times would I still need to do this? Sharing my desktop. Not very much. Okay, sharing my desktop. Yeah. Okay. So chapter 8 is on second order circuits. Remember, chapter 6 we introduced the passive elements, inductor and capacitor, and it turned out that their definitions involve derivatives, right? So when we went to chapter 7 and we started applying all the circuit principles and techniques that we've learned, the equations turned out to be differential equations, right? Every time you have a capacitor, there's a derivative involved. Therefore, if there's only one capacitor or inductor, we end up with a first order differential equation, right? So in chapter 8, this should be called second order or higher circuits, we will see. A second order circuit is one in which you have 2 storage elements, either 2 capacitors or 2 inductors, or one of each, okay? If the capacitors can be simplified to a single equivalent, sometimes you can do that, especially if the capacitors are either in series, parallel, or delta Y or something, right? And there's no resistors and other sources in between them, you can combine them to a single, right? So technically, those would still be first order. So if you cannot simplify, after simplifying all the capacitors and inductors, you have either 2 capacitors, 2 inductors, or 1 of each. You can be sure that it's a second order circuit because you have 2 storage elements. Okay, and for each storage element, you can have a derivative. Since you have two storage elements, you can end up with a second order differential equation. Now, those of you who have taken differential equations, whenever you have a second order differential equation, in order to find a specific solution, you're going to need 2 initial conditions, right? Yes? And those initial conditions usually are what? Regarding the initial value of the variable and the initial value of its derivative, right? And most of the time in differential equations, those initial conditions are given. Yes? In this class, yes, we're going to solve second and higher order differential equations. Sometimes you actually have to set up and find the differential equation, solve it, and the most difficult part really is finding the initial conditions. Okay, so that's the part that makes it slightly more challenging than differential equations because we have to find our own initial conditions. Okay. So before we do that, just in preparations for finding initial conditions, because that's actually the most difficult part, we're going to review something that we have done before in chapter 6. Finding final values or steady state values of your voltage for a capacitor and current in an inductor. And how do we do that? Steady state values. Under steady state conditions, capacitor becomes an open circuit and an inductor becomes a short circuit. Yes? And then you just find whatever variable you're looking for. Okay? Now, in terms of finding initial values of variables, usually if it involves a capacitor, we're obsessed with the voltage, right? And there's two reasons, right? Because the voltage of the capacitor determines the energy, and consequently, what? Because of continuity of energy, the voltage in the capacitor doesn't jump. Okay. On the other hand, for an inductor, it's the current that determines its energy, and it's also the current that doesn't jump. Okay. So, but the finding initial conditions always come from the no jump condition or continuity of energy, which states that what? For a capacitor, the voltage before and after, usually the initial is at t equals 0, and the continuity of energy condition says that even if you flip the switch or change the configuration of the circuit, okay, the voltage before and after that t equals 0 should be the same for a capacitor, and how is it, bro? The current for inductor doesn't jump. Okay, we all know that. Okay. The challenging part is, in addition to finding initial conditions, we actually know how to do this in chapter 7. Yes, because in your general first order solution, you have B of a capacitor equals V infinity plus V naught minus V infinity e to the minus t over tau, right? We know how to find V naught on our own, right? Same thing for IL or I naught on our own. In addition to finding initial voltage and the current, okay, if you remember what I said about differential equations, you have two initial conditions, and the initial conditions usually pertain to initial value of a variable and the initial value of its derivative. Yes? Those pairs, that pair of initial values actually are supplied by your differential equations teacher when they're asking you to solve a second order differential equation. Yes? For us, we'll have to find those initial values of derivatives, and those could be challenging. Okay? Here, let's look at an example here. Find, I don't like, math teachers will actually have a fit on that, V sub C infinity, but we know what that means, right? It's the steady state value of a capacitor's voltage, right? So it's really what? V sub C as t approaches infinity, right? It's a limit rather than V sub C infinity. We're asked to find steady state value for the voltage of the capacitor, current in the inductor, and voltage across the 2 ohm resistor in the circuit for the first part. Second part will be initial values for those variables, and third part will be initial values for derivatives of those values. Okay? So part 1 of this problem shouldn't be very difficult because you did a lot of this already in chapter 6 and even chapter 7. Yes? Okay, so for part A, we are really looking for steady state values, and under steady state, what happens to a capacitor? Okay, it becomes an open circuit, and what happens to an inductor? It becomes a short circuit. So I will redraw this at infinity, okay, and at infinity is the current source on at infinity. Yes, why? It's a step function. It comes on right after t equals 0 and stays on until infinity, right? So I will redraw the circuit as having, instead of showing that it's 3u of t, it's actually just 3 amps now, yes? It assumes a specific value of 3 amps because I'm looking at it for t greater than 0, okay? And then I have my 2 ohm resistor here, and then I have my 4 ohm resistor here. And what happens to the capacitor? I'm looking at steady state. What happens to the capacitor? It becomes an open circuit, right? And of course, I always have my 20 volt source here that's always on, T less than 0, T greater than 0. And then I have my inductor here. What happens to the inductor? Short. Coming from me, it doesn't sound as bad. Okay. And we are looking for, what are the three things that we're looking for in this diagram here? Okay, current through the inductor, that's what we're calling IL infinity or I infinity, right? And the voltage across the capacitor, that's what we're calling V infinity. Maybe I should put a subscript there somewhere. Okay, let's just use the nomenclature that they're using. So it's going to be IL infinity, right? VC infinity, and what's the other one we're looking for? Voltage across the 2 ohm at infinity. Okay? And as I promised, this should not be too bad, right? Because after I do that, it becomes like a chapter 2 or 3 problem, right? It's just, you can use whatever method you want, okay? But it's easy to see that what is the value of IL infinity? Or what's the value of V sub C? Which one do you want to work on first? Okay, let's do IL infinity. How would I find IL infinity? The easiest way of finding IL infinity. So this part here is open, and this is a short, which means that the 4 and the 2 are just in parallel. Is that okay? And we have what? A current source of 3 being divided into 2 parts. One goes to 4 and the other goes to 2 ohms. What's the best way of finding that? It's current divider equation. By using current divider equation, IL infinity would be using our method, not the books. It's 1/4, right? It's the conductance of the element that you're interested in divided by the total conductance, which is 1 plus 1/4 multiplied by the total current that you're dividing. So that's going to be how much? So I think it's going to be 1 amp. Not because I am quick. I'm just doing a quick ratio and proportion here, right? This is twice as this, right? Therefore, the current in the bigger conductance will be twice the current in the smaller conductance. Therefore, of the 3, 2 is going to go to the 2 ohms and 1 is going to go to the 4. That's why I said it's 1 ohm. Okay? 1 amp. Based on that, what is my VC at infinity? Oops, let's change the color now. Can anyone tell me what VC at infinity is going to be? I was going to change to this. Voltage across the inductor is 0. The open will, and the 20 will be 0, which means that VC at infinity must be negative 20. Everyone okay with that? So there's 2 ways of doing that. You can do a KVL on the right loop. The KVL will tell me minus 20 minus VC infinity equals 0. Yes, because there's nothing on the right. Therefore, VC infinity is negative 20. Is that okay? Or some of you would rather look at this as node voltages, right? So if this is my ground, what's the node voltage here above the 20 volt source? Is going to be 20, right? What is the node voltage up here? According to the fact that the inductor is short, the node voltage up there must be 0. Yes? Everyone okay with that being 0? Because this wire here, that is the inductor, being a short, is connected to that. So how do I go from 20 to 0? The V sub C infinity must be negative 20. Yes? Because I'm going from 20 to 0. Okay. Finally, what is VR at infinity based on this picture? So we already know that the branch that goes through inductor, which is the same branch as the 4 ohm, is getting how much current? 1 amp. Therefore, here would be 2 amps. Yes. So what is VR infinity? It's going to be 2 ohms, right, multiplied by, it's 2 amps. The 1 is through this. And you have 3, right? So 2 must be going through the 2 ohms. So it's going to be 4 volts. Everyone okay with that? And as I said, that part should not be shocking to you. You've done that in chapter 6 and 7. Yes? Finding steady state value. You do that all the time in order to set up our equation for first order, right? In fact, the second part of the problem also is not that difficult because how much room do I have? I will do it here, okay? So for part B, we're asked to find what? Initial values of the same 3 variables. So for part B, we are looking for V of C at 0 plus, I of L at 0 plus, and V of R at 0 plus. So it's initial values we're looking for, and initial values, if they're not given to you, where do you get them from? Where do IC's initial values come from? Yeah, the circuit at T is 0 minus, and that's because of what? The no jump condition, right? And the no jump conditions are what? V of C at 0 plus is the same as V of C at 0 minus, okay? And I of L at 0 plus is the same as I of L at 0 minus. And what's the no jump condition for a resistor? There is none, okay? So even though I'm interested in VR at 0 plus, I do not apply a no jump condition for a resistor because for a resistor, in both voltage and current can jump, okay? So the no jump conditions will just be these two. So what that means is we need to look at the circuit at T equals 0 minus. Okay? What does the circuit look like at T equals 0 minus? Do you understand why I'm looking at T equals 0 minus? Because the initial condition is not given, and we're going to take advantage of what? The no jump condition for voltage of a capacitor and current in the inductor by looking at what those values are before T equals 0. Because those should propagate to T equals 0 plus. So at T equals 0 minus, what can I say about the current source? Oops. So is the current source on at T equals 0 minus? No, right? Because of the U of T. Remember U of T, the unit step function means that it's 0 for T less than 0. Right? So that means is we need to turn off or remove the current source. And how do we do that, Victor? Yeah, it's open. Right? It's voltage source that is short and the current source that you open. Okay, how do you not forget that? So when you're removing a current source, you want to make the IS 0, right? The current got to go to 0. What element has 0 current? An open circuit. Does that make sense? So when you're removing a voltage source, you want to make the VS 0. What element has 0 voltage? A short. Okay. Okay, so I think at one point you just sort of memorized it, and now it's when you just memorize something, it's as easy to unmemorize it, you know. So try to put some logic, okay? So that means this is an open, right? Okay, and here's our 2 ohm resistor, okay, and here's my 4 ohm resistor, And here's my capacitor. Oh, we're going to assume again that at t equals 0 minus, what? The circuit has been there for a long time, so steady state again, which means that the capacitor is open again, right? And whatever that voltage across that open is going to be our VC 0 minus, okay? And then here's our 20 volt source, okay? And here's our inductor. Again, we're going to assume that it's been in this condition for a long time, so steady state again, and we replace the inductor with a short, so whatever that current is through that inductor is IL 0 minus. Everyone okay with this circuit? How I got it? This is open circuit, and it's steady state, so the capacitor is open and the inductor is short. Okay? Take note that I only label these two variables here, VC and IL. I don't even bother solving for VR at 0 minus, even though I know that the problem is asking me to find VR 0 plus, because that value of VR 0 minus will not have a direct effect on the value of VR 0 plus, because it's going to jump. So the only variables I label here, okay, intentionally are the variables I know are not going to jump. Okay, so help me find those two variables. What is IL at 0 minus? Anyone? After calling somewhere. Oh, somebody sent me an email. Okay, so what's the value of IL at 0 minus? So there's only one source, the 20 volt source, but it's not connected to that wire, right? So IL is 0. Everyone okay with that? Yes. There's no way for that source to send any current anywhere. It's actually not connected. Okay? Bianca? Yes. Okay. What is in? What did you say? So the three elements in series are the 2 ohms, the 4 ohms, and the short. Yes? The 20 volts is not connected to any of those elements, because the 20 volts is not across the 4, the 2, it's not across the 4 and the 2, right? Because there's an open here. I think you got confused. You forgot about this open. Are we okay? Okay, so it's 0. Yes? Okay, and consequently, what is V of C at 0 minus? For a different reason, it's also 0, right? But the reason for that is the same reason as we had before, the KVL here, the fact that the inductor is a short. Yes? Are you okay with both being 0? Okay? Now, why did I do that? Because those two values will not change. So the IL at 0 plus will still be 0 amps, and VC at 0, whoop, we don't want that happening again, 0 volts. So that takes care of this too, right? But it doesn't take care of VR at 0 plus. And I don't look for VR here at 0 minus, because that can jump. Okay? So what I need to do now is what? What do you think I need to do now? Look at the circuit at t equals 0 plus. Yes? Because I'm still not done with part B, right? I still need to find VR at 0 plus. Yes? And that will only show up in the circuit at t equals 0 plus. So how is the circuit now different from the circuit at t equals 0 minus? The current source suddenly becomes active. So this is 3 amps here, right? This is my 2 ohms here. This is my 4 ohms here. In addition to that, okay, at t equals 0 minus, what? We're not at steady state anymore. Therefore, the capacitor is no longer an open. Yes? So I need to draw the capacitor. The source is still here, 20 volts. And then, similarly, since at t equals 0 plus, the inductor is no longer a short because we're not at steady state anymore, right? Are you okay with the circuit I have here? So in addition to the 3 amps being on now at T equals 0 plus, okay, the capacitor is just now a regular capacitor. It's no longer open, and the inductor is just a regular inductor because we're not at steady state. So you're only steady state at T equals 0 minus and at infinity. At T equals 0 plus, you're not anymore. Okay? But yes. T equals 0 minus right here. And I know that it's been there for a long time. That's why.
And the one before that, that was T before it.
Infinity, yes.
That's steady state.
Steady state, yes, greater than 0. Okay. This is also steady state, but it's right before 0.
Oh, okay.
Both of them are. Correct. As soon as you turn this on, okay? And nothing steady state at 0 plus, okay? So what we do know at T equals 0 plus, there are only 2 things we know about 0 plus. And what are they? Yes, the 2 no jump conditions. Right? So these 2 things that I found here, okay, we'll go to T equals 0 plus because of the no jump condition, which means that, yes, the inductor is no longer a short, okay, however, the current there at 0 plus will still be 0, right, because it was 0 before. Similarly, the capacitor, yes, it's no longer a short, it's no longer an open, but the voltage across it is still 0 volts because of no jump condition. Yes, Ian. Uh-huh. This one? Uh-huh. Okay, it's okay because I did a KVL on this loop. Minus 20 minus VC equals 0. Is that okay? It's negative. Oh yeah, it's negative 20. Yes. Sorry. Yeah, yes, thank you. Okay. It's negative 20. Okay. Okay. Thank you so much. I cannot believe people didn't point that out there. So I already, the reason I skipped that was because we went through that solution earlier. And I was just supposed to copy whatever we had here, and I copied the wrong thing. Okay? Thank you. Now I'm getting worried. Anyone else confused about that earlier?
Yeah, I was like thinking, like, I really
Okay, so everyone's okay that it should be minus 20, the same reason as we had before, okay? So that means this is still minus 20. Okay, thank you. Equals minus 20 volts. Okay. So you okay now? So, and we're looking for, what are we looking for at T equals 0 plus? VR at 0 plus, which is the voltage here. And does anyone have any ideas on how I can find that? What is VR 0 plus? I do not know what you mean. Oh, you mean the voltage here is 0? Okay, so, okay, hold on a second. When you're talking about the inductor, be careful about using its voltage because the voltage in an inductor can jump. Okay, only the current. So the only thing we know initially is the current here in the inductor is 0 and the voltage across the capacitor is minus 20. However, if you want to analyze the voltage across the inductor, okay, you have to borrow the property of the capacitor that says that it cannot jump. Okay, if voltage across the capacitor is still minus 20, what that means is node voltage up here would still be 0, which means that yes, the voltage across the inductor is still 0. But it's not because of the inductor, it was actually because of the capacitor. Okay, so capacitor controls voltages, inductors control currents. Okay, so yes, indeed, in this picture here, the 4 and the 2 are going to be in parallel. Not necessarily because the inductor is short. The inductor is not short anymore because we're not in steady state, but more because what? The voltage across the series combination of the capacitor and the 20 is still 0. Yes. Okay? Everyone okay with that? So what's our VR at 0 plus, therefore? You can do current divider now, again, like we did earlier. So out of the 3, how much is going to go across VR? 2, right? Therefore, what's VR 0 plus? There's going to be 4 volts. Okay? Or if you're not comfortable with that, we can just do a couple of KVLs or KCLs. But I think it's pretty clear, right? If you didn't know that, that's what? Oh yeah, you can do a KVL over. So you can do mesh if you want. So you can. So if you're really confused and you don't want to go through these hand waving things, you just always rely on your KVL, KCL, or your nodal and mesh. They will always work. So for instance, if you do mesh, the mesh number 1 here is 3, right? Mesh number 2 you don't know, right? Mesh number 3 is 0 because of the inductor, and then you just do a mesh in the middle. It will tell you what the mesh current there is, and then you can find VR, right? So none of this hand waving arguments in the meantime. You just use the fact that IL here is 0, and then the KVL here will make use of the minus 20 here and the plus 20 will. Okay? So everyone okay with that? Finding initial conditions. So for inductors, current and the voltage capacitor, and the capacitor's voltage, nothing new because we did that in chapter 7, right? When you're doing the V infinity plus V naught plus V infinity, yes? And I naught, right? It's only when you're looking at another variable, such as the resistor's voltage, that we can have to look at this, the picture before and the picture after, in order to find that value, because that VR doesn't jump. The VR actually jumps. Right? It does not. It's not subject to continuity of energy. Okay? Because what's the value of VR at 0 minus? It's 0, right? There's no current anywhere. You agree? Okay. And what's the value of VR at 0 plus? It's 4, and clearly it jumps, and it's okay because for a resistor, anything can jump. Okay. Now let's go to part C, and part C is what? Finding initial values of derivatives. Okay. So I think the way the book labeled this is funny. That's the one that would really give a heart attack to your calculus teacher. I think the book says something like this: derivative dV/dt at infinity of. That's yeah. Even I will have a heart attack, right? Because it appears like you're finding the steady state value and differentiating. Of course, the value will be 0, right? Yes, but what they really mean. Yes, because you evaluate do you understand what this means? You evaluate C at V sub C at infinity, and then you differentiate that. Of course, VC at infinity is a constant, and when you differentiate that, it's going to be 0, right? So I think the authors of the book, or at least electrical engineers, don't understand that. But what they really mean is what? It's the value of the derivative of the voltage as a function at time, evaluated at infinity, right? That's what that, not infinity. It's actually 0. It's really not. I messed up. The book actually has this. That's what the book has, right? Initial values of the derivative. Yes, not infinity. It's the initial values of the derivative. Yes. So the book has this as the symbol, which sort of makes sense, but it really doesn't, right? Because according to that, what is it? Evaluate v at t equals 0 plus and differentiate it. But v at t equals 0 plus is going to be a constant. When you differentiate that, it's going to be 0. Yes? What we really want is the value of the derivative evaluated at t equals 0. Okay? You understand the difference? So let's just pretend that the book is okay. So for part C, what are really the things that we're looking for? It's the value of the derivative of C evaluated at t equals 0 plus, right? The derivative of the current IL at t equals 0 plus, and the derivative of VR at t equals 0 plus. Okay? And do you understand the motivation for having to find these things here? Other than to torture you? Why do we need this? Because it's a second order differential equation, and you're going to need two initial conditions in order to evaluate the two constants of integration. And if you remember from differential equations, those two initial conditions are always the initial value of the variable and the initial value of the derivative of the variable. Right? In differential equations, that's what we've taken. Right? So we need to be able to find this on our own, because unlike differential equations, I'm not going to give you that. I'll give you the circuit, and you're supposed to figure that out. Okay? And this is probably the part that is the most challenging the entire course, actually. I'm going to tell you right now. Because there's a lot of hand-waving, and the actual solution just depends so much on what the circuit looks like. Okay? But don't worry, it's just a small part of the whole chapter 8. And in order to maximize your points on the test, I will tell you exactly what procedure you should do and not follow the book, because the book wants you to start with this. And a lot of times if you get stuck with this, the rest of the solution you can't do. Okay, so the way I'll tell you to is solve the differential equation and leave the initial conditions at the end. Because at least the first part in the solving of the differential equation is actually sort of mechanical. So hopefully that will give you confidence that you're not going to lose all the points. Because if this is the first thing you try to do, and it is the most difficult part, you basically lose the whole problem. Okay? Okay, so let's find dBc dt at t equals 0 plus, dIL dt at t equals 0 plus, and dVR dt at t equals 0 plus. And which circuit do we look at? It's the same circuit at t equals 0 plus. That's why I don't have a lot of room here, but I'm going to do it right here, because I'm going to be looking at this. Okay? Now, in finding dVc dt and dIL dt, those are actually easier to do. You know why? Have you seen an expression dVc dt before? That's actually coming from what? At any time I sub c is equal to c dVc dt. Yes? This is true at any time. Yes? This must be true at t equals 0 plus. So I'm going to take advantage of the definition of I in the capacitor and say that at any time dVc dt is just equal to what? I sub c over c. Yes? Okay? I'm just solving. And then this is true at any time. It must be true at t equals 0. So I just evaluate this at t equals 0 plus, right? This becomes 0 plus. So this actually gives me what? A sort of direct way of finding dVc dt at t equals 0 plus. All I have to do is what? Find I sub c at 0 plus and divided by C. Okay, so how do I find I sub C at 0 plus? I will look at the circuit and look for the current with the resistor at 0 plus. Yes? Okay, so what is that current, you think? And no, it's not 0. Okay? Why is it not necessarily 0? Because the capacitor is not open. It was only open at t equals 0 minus, at t equals 0, t equals 0 plus. It's what? It's the current flowing to the 4 ohms. Why? The current in the inductor is 0. Therefore, how much was flowing to the 4? It was 2 amps, 1 amp, right? Can only go through the capacitor. Why? Because the current in the inductor has to remain 0. Okay? So I sub C at 0 plus is actually what? How much? Whoops. 1 amp divided by, what's the capacitance? 1/2 farad. So it's going to be 2 what? Volts per second. Did everyone? So how did I find out again? So I'm looking for a current here. So I was doing a KCL here. Right? I already know the current here to be 1 amp. Why is that 1 amp? Because the 3 gets divided into 2 amps goes to the lower resistance. 1 amp goes to the higher resistance. Therefore, there's 1 amp here that has no choice but to go through the capacitor. Why is that? Because the inductor's current has to remain 0. Again, when you're looking for a current, even though it's the current in the capacitor, currents are actually controlled by inductor, because the current in the inductor is the one that doesn't change. Okay? Now, similarly, what do you think is the best way to find DIL dt? Have you seen a DIL dt before? Yes. From the definition of an inductor, VL is equal to BIL dt. Yes? This is true at, what happened? This is true at any time. Okay, so I solve for DIL dt is going to be G sub L over L. That's true at any time. Therefore, it must be true at t equals 0 also, right? So at t equals 0 plus, I can say that if I want to find DIL dt at t equals 0 plus, all I have to do is find the voltage across the inductor at 0 plus and divide it by the inductance. Okay, and what's this value? We sort of kind of saw that earlier. What's the voltage across the inductor at t equals 0 plus? If you forgot, you just do a KVL here, right? And the KVL will tell me minus 20 plus VL at t equals 0 plus equals 0. Because the VL at 0 plus, what we're looking for is really over here, right? Yes. So KVL, remember we established that the inductor's voltage still 0 earlier, right? And it's not necessarily because of the inductor, it was actually because of the capacitor right next to it. That cannot change. Okay? So VL of 0 plus is 0, therefore the IL dt at 0 plus will be 0. We can put units just to amps per second. Are these two okay? So as I mentioned, the first two are really not that bad because the derivatives that we're looking for pertain to variables that we've already seen before, right? We've seen dVc dt before in the context of the definition of the current in the capacitor. We have seen DIL dt before in the context of voltage in the inductor. However, VR, the definition of VR does not involve any kind of derivative. Yes? Okay, so any suggestions on how we should find dVR dt at t equals 0? So you understand why these two are slightly easier, because they are built in our definitions for the capacitor inductor. For the capacitor's voltage derivative, we just need a current, and vice versa. But we don't have such a definition for a resistor that involves derivatives, right? The definition of resistor does not involve a derivative. It's V equals I. Okay, so any ideas on how to find dVR dt at t equals 0 plus? That's why we have this whole room, okay? So it's dVR dt at t equals 0 plus. How do we find this? So in fact, if the problem was asking us to find, let's say, if the problem was asking us to find dic dt, we will be in trouble also, right? Yes, because we don't have anything that involves the dic dt. Same thing, if the problem was asking us dVL dt, we don't have anything for dVL dt. We have a dIL dt, right? So in those instances, how would you do it? It's very similar to what our approach is going to be with respect to this, because the definition of VR does not involve any derivatives. Okay? So any suggestions on what we should be doing? So remember, we're trying to look for the initial value of a derivative. How would you do that? So I think the only correct mathematical way to do that is find an expression for VR that is true at any time, and then differentiate with respect to time, and hopefully you can find that value. Yes? Because we don't have anything that involves the derivatives of VR outright, right? So what we need to do is find an expression for VR that is true at any time. Then we're going to differentiate that equation. We're going to have a dVR dt in that equation. Yes? And then we evaluate at t equals 0. Hopefully we'll find the value. Okay? But how do we do that? So do you understand my plan? I'm going to look for an equation that involves VR that is true at any time. Okay? And I'm going to differentiate that. And God help me, hopefully when I evaluate at t equals 0, it has a value. Okay? How do we do that? So let's copy the circuit at any t. At any t that's greater than 0, I will look for an expression for the voltage. Okay, so help me reconstruct the circuit at any time t. So I think the 3 amps is on here. Yes? And then, do we have a 4 up here? Oh, I forgot already. Oh, it's between that and the 2. Okay, so there's a 2 first. I'll just do the 2 here. Alright, this is the 2, and this is the VR, right? And then I think we had the capacitor here, and then the 20 volts here, and then we have the inductor here, right? Okay, so we want to find an expression for VR that's true at any time, okay? However, as soon as I differentiate it, I'm going to have a problem, because that expression for VR as a function of time will involve another derivative, because I'm differentiating it, and I'm counting on the fact that I should be able to find that derivative. Yes? So my plan, here's my plan. I'm going to look for an equation that involves VR that is true at any time. And that's the reason why I'm looking at the circuit at any time. And after I have that equation, I'm going to differentiate that. Of course, that equation will have VR in it and some other variable in the circuit, right? Some other current and voltage somewhere else in the circuit. And then I'm going to differentiate that equation. Of course, when I do that, I will have a dvr dt, but I will also have derivatives for other variables in my equation, whatever equation I used. So my hope is when I do the differentiation to find dvr dt, the other derivatives that will come out from the differentiation will involve things that I already know, or things that I can find. What are the derivatives that I already know I can find? dvc dt, right, and dil dt. So what that means is, as I look for an expression for VR, I'm going to try to relate that to either the voltage across the capacitor or the current in the inductor, in the hopes that when I differentiate that equation, okay, I will be able to find the value of those derivatives on the other side of the equation. Does that make sense? Does that sound like a plan? Okay. So how do I relate? So I somehow need to relate it to what are the two variables that are useful for me? IL, right? Because I already have the IL dt, right? And what's the other variable? VC. Right? So somehow I need to find an equation that involves this VR and relates it to either VC and IL. Okay, and even both of them is fine, right? Because both of those derivatives I already know. So how would I do that? Well, you can use any circuit principle that you want. So any suggestions? Bless you. Any suggestions on how mesh would work? The problem with mesh, okay, maybe. The problem with mesh is it's going to involve both, right? Yes. It's going to, so if I can do away with defining new variables like I1 and I2 and just stick with the VC and the IL, that's going to be easier, right? Because you don't want to involve other variables. That means I have to find a way to find those derivatives also, right? Whenever possible, just stick with these two variables. Why? Because I already know what those derivatives are at t equals 0. Yes. So I agree with you. Probably it's going to work, but it's not a good idea because it's going to involve new variables. And you're going to have to figure out, how do I find those derivatives? So can we just stick with this too, if possible? Okay, any other suggestions? Okay, so we could do nodal. Is that what you're going to say? It's either usually nodal, KVL, KCL, or mesh, right? I don't like the mesh because it creates new variables, right? I like nodal. Why? Because one of the variables is directly VR, right? And the other variable here, you just need, what's the node voltage here? Is it DC? No. This is at any time t. It was 0 only at t equals 0 minus and 0 plus. This is at any time t. What is the node voltage up there? It's not quite VC, but you're close. 20 plus VC, yes. The node voltage here is 20, right? And this side of the capacitor is VC higher than the 20. Therefore, this is, are you okay with me saying this is 20 plus VC? Yes. And I think that's what we're looking for because now I'm ready to do a nodal, right? Nodal for which one? Nodal for VR. What's the nodal for VR going to tell me? 3 amps positive, right? Plus 0 minus VR divided by 2 plus 20 plus VC minus VR divided by, what's this? 4 is equal to 0. Everyone okay with that? I like that rather than regular KVL or KCL because if I do a regular KVL here, it's going to involve a current here in that resistor, and I don't want to introduce another variable that will have me worry. I think this is perfect, right? Because number one, it has VR in it. That's true at any time. Number two, it has VC in it. And I know that I can find the value of the derivative of VC because dVC dt is just I sub C over C at any time. Yes? No, I'm doing a nodal here. Okay? And that's the reason why I didn't do nodal here. Because that will involve I through the capacitor. Right? Okay? Everyone okay with this? And this is ideal. Because I know that it's true. So let's simplify this. If you want, you can solve for VR. So multiply everything by 4. What would it be? This is 12. You better watch my... And this is going to be minus 3VR. Is that okay? Plus 20 plus VC is equal to 0. Did I do that correctly? Multiplied everything by 12. So where did I get that? No, not 12, but by 4, right? So where did I get the 3? It should be 2. Oh yeah, I added it. See, I'm confused. And it's correct, right? Okay, so I multiply everything by 4, so this becomes 2, but I have another 1 here. So that's why it becomes 3. It's correct. Okay, so what this tells me is that VR at any time is equal to, what is that, 32 plus VC over 3. Yes? Okay? And we know that that is true at any time. And that's what I wanted, a V expression for V that is true at any time, because now I can differentiate that, right? So if I differentiate the equation, what will I get? dVR dt must be equal to what? What's derivative of 32 over 3? 0 plus 1/3 dVC dt. Okay? And that's true at any time. It has to be true at t equals 0 also. So dV dt, so dVR dt at t equals 0 plus must be equal to 1/3 of dVC dt at t equals 0 plus. And don't we know dVC dt at t equals 0 plus already? Right? And if we still don't, we can find it, right? What is dVC dt at t equals 0 plus? It's I sub C at 0 plus divided by C, right? Which you actually already know earlier. What was it? It was 2 because it's 1 divided by 0.5, right? 1 has the capacitor. So this was 2 volts per second. So our dVR dt at t equals 0 plus is 2/3 volts per second. Okay? Is this problem clear? Okay? So what makes this slightly more difficult than previous topics is you have to be a little creative, you know. But if you have, our objective is find an expression for VR that involves exclusively either V sub C or I sub L, or both. Why V sub C and I sub L? Because I already know the values of those derivatives at t equals 0 plus. And the way you do that is so dependent on what the circuit looks like. Okay? And also the dangerous thing about this when you start working on the problems is you might get the correct answer, but your logic is actually not correct. It just so happens that your answer is correct. Okay, and common mistakes are mistakes as you go from 0 minus to 0 plus. Okay, at 0 plus, it's not steady state, so the capacitor is not open, the inductor is not short. Okay? Okay, so that's only to find initial conditions. We haven't really solved any circuit yet. But promise, that part is the most challenging one, only because it's not procedural. It will depend on what there's a lot of hand waving involved. Okay, so I'm not going to deny that's the most difficult part, but it's okay. So we're going to start looking at the actual circuits now. The first one we're going to look at is source free. What makes it source free? No independent sources, right? And it's going to be a second order circuit because in this case we have one inductor and one capacitor, and they happen to be connected in series. Okay, so let's solve this circuit here. So let's say that I'm interested in the current in the inductor. Oh, okay, it doesn't tell me what I'm trying to find. Let's say I'm trying to find, what do you want to find here? What variable makes sense to find here? Which one? VC as a function of time or IL as a function of time, right? Which one would probably make even more sense compared to the other? Probably I. Why? Because IL is the same for all of them, right? But take note, if I know IL, I know IC, which means that I can find VC and vice versa. Okay? But we're going to focus on I and take advantage of the fact that they are in series, right? When the things are in series, there's only one I. Let's solve for that I. Okay? So find I as a function of time for t greater than 0. So luckily for us, we're given the initial conditions. IL at 0 and VC at 0. Okay, so taking advantage of the fact that they are in series, okay, I'm going to do a KVL. Okay, starting from the left, what would be my first term? Positive R times I, right? Plus, oops, it's not a resistor, so what do? I probably should call this V sub L for now. Yes, so I'm going to say V sub L. Similarly here, this is going to be V sub C is equal to 0. Okay? And you understand, I did a KVL, it just so happens the two elements are not resistors. So instead of saying R times I, I'm just saying voltage across the inductor and voltage across the capacitor. Right? However, I can express that voltage across the inductor in terms of the current through the inductor. What is V sub L in terms of I sub L? Okay, it's L di L dt, but di L dt is just di. Okay, how about V sub C? Can I express that in terms of I? Okay, it's 1 over C, the funny integral from minus infinity to t of I dt. Everyone okay with that? Where that came from? That came from what? I sub C is equal to C dVc dt. Right? I sub C is the same as I because they're all in series, and if I'm looking for VC, I need to integrate. Okay? So if I do that, let's oblige and do that. My KVL now is RL plus LDI dt plus 1 over C integral from minus infinity to t of I dt equals 0. So what have we achieved here? Well, instead of having 3 variables in our equation, we had 3 variables initially, right? I, VL, and VC. We only have 1 variable, right? That's That's an achievement, right? One variable, one equation. Isn't that nice? However, our equation is now, what would you call this equation? It's called an integral differential equation. Why is it called an integral differential equation? Because you have an integral and a differential or a derivative, right? So it's called an integral differential equation, but I don't know. Have you guys taken the math 275.5? It's called integral differential equations. You haven't, right? Integral differential. You have not solved integral differential equations, right? Okay. So what do we do? Derive, you mean differentiate, right? So I can actually turn it into just a regular differential equation by differentiating the whole equation with respect to time again. Okay, so the first term becomes R, oops, that's not L, right? This is I, yes? Oops. R di dt, yes? Plus L, what's the derivative of di dt? D squared I dt plus 1 over C times, what's the derivative of an integral? It's just the function itself, right? So it becomes I equals 0. And that's the reason why we differentiated in order to get rid of the integral part of the equation. Everyone okay? How I got from here to here? Derivative of an integral is just the function itself. Okay? So this is now, what is this? It's now a regular, ordinary differential equation. It's second order, right? And it's homogeneous, right? 0 on the right, okay, for differential equations people. And also linear. What does make this linear? What makes this linear? There is no product of I with itself or with its derivative. Right? You don't see di dt times I or di dt squared times I and so on and so forth. So it's linear, homogeneous second order, and also it's constant coefficient. Right? The coefficients of the terms are constant. So I will rewrite this in descending orders of the derivatives. So L d squared I dt squared plus R di dt plus 1 over C I is equal to 0. Okay? So I'm not going to write, and no, it's not separable anymore. Separable differential equation all apply to first order. This is now second order. So the way we're going to characterize this is it's a second order homogeneous differential equation, right? Homogeneous because 0 on the right side, and it's constant coefficient and linear. Okay? Now with all those terms, yes. No, it doesn't matter. So he's suggesting divide everything by L actually, right? R over L becomes a tau, which we already know. L over R, but let's not do that, okay? And let's not even do a tau at this point. So it's not separable anymore. But differential equations, people, you have always of solving this, right? It's okay. But for non-differential equations, people, let's just look at what it's saying, okay? So how many of you have not taken differential or feel like they have not taken differential? Okay, let's look at this equation here, okay? Just focus on what the equation is asking us to find. So we want a function I that's a function of time, right? Such that what? Some linear combination of I with its derivatives, first derivative and its second derivative, always goes to 0 all the time. Right? That's what it's saying. Right? So we are looking for a function I such that if we add it, except for some constants, right, L, R, and 1 over C, we are able to cancel I with its derivative and its second derivative at any instant of time. Right? That's what this is saying. So if you think about it, can you think of a function that has the ability to do that? The exponential, right? Because in order for you to cancel the function and its derivative at all times, okay, the function and the derivative should be of the same form, right? Because a sine function cannot cancel an exponential, and an exponential cannot cancel a polynomial, right? So at least at the minimum, you expect a function whose first derivative and second derivatives will be of a similar form as the original function. Why? Because they're able to cancel each other. Okay, so we're going to say, I know of a function that behaves like that. So I'm going to try that function. So I'm going to try an exponential function. What is the general form of an exponential function? Okay, so you have a constant multiplied by e to the st, right? Where a and s are constants. This is the general form of an exponential function. So we're going to try that. Why are we trying it? Because we suspect that it's a function that will satisfy this. Why? Because its derivatives and first and second derivatives are also exponentials, and therefore they can potentially cancel each other. Okay? So when I do that, so if I a e to the st, what is di dt? So it's going to be a s e to the st, and as we suspected, it's also an exponential function, right? Whereas d squared I dt squared is what? Okay, a s squared e to the st. Yes. So if we substitute I di dt and d squared I dt squared into the differential equation, we're going to get something like L times, what is our second derivative is a s squared e to the st plus r di dt, which is a s e to the st, plus 1 over c times our I, which is a e to the st, is equal to 0. Right? At this point, I am really not sure if this is going to be solution. I just suspect that it could be. Okay? And then, this has to equal 0 all the time. So, when you're solving a function, an equation, 0, what do you do according to algebra? Factor the greatest common factor first, right? So, what's the greatest common factor? Okay, so the greatest common factor is a e to the st. So, the first part will give me ls squared plus rs plus 1 over c is equal to 0. Okay? And then, according to algebra, you equate its factor to 0, right? E to the st is never 0, right? Exponential function never crosses the x-axis. A could be 0, but that will give you the 0 function. It's called the trivial solution. If a is 0, your current is 0 all the time, right? If your current is 0 all the time, of course, it's going to satisfy that. Okay, so the only non-trivial solution is going to come from that quantity in the brackets be equal to 0, and that's going to be ls squared plus rs plus 1 over c is equal to 0. Yes, we're going to have to use a quadratic formula. And take note that this equation here in differential equations is what you call the characteristic equation for the differential equation. Why is it called a characteristic equation? It just is. Well, so in the context of our problem here, it really characterizes the circuit. Okay. It characterizes it because it depends on what? The values of the LRC, right? Those are characteristics of the circuit. And also the way we connected them, they are connected in series, right? So it characterizes the circuit. It has nothing to do with time, right? This doesn't know about time. It just tells you something about the characteristic of the circuit and how you connected them. That's why they're called characteristic equation. Okay, so of course it's a quadratic equation, and we can solve the roots of those quadratic equations. So in general, you can have up to 2 solutions, right? So it's going to be negative b plus or minus the square root of b squared minus 4ac. Does this look familiar? Divided by 2a, your quadratic formula. Yes. What is a in our case? Oops. Oops, I skipped a page. So here's our A. So can you remember? A is L, R is B, and 1 over C is C. Small c's. Okay. So S12 is equal to negative B plus or minus the square root of B squared minus 4AC divided by 2A, where A was L, right? B was R, and small c is 1 over big C. Yes? So let's substitute that here. So it's negative B, which is R, plus or minus the square root of B again, which is R, but we need to square that, minus 4 times A. What is A? L. And then what is small c? Is 1 over C. All divided by 2L. Okay? Now I'm going to distribute the numerator into the denominator. You agree it's going to be minus R over 2L. Yes? Plus or minus the square root of, I'm going to make the 2L go inside the square root. I know your algebra teacher, at least mine, said you cannot do that. You can have fractions inside of, did he still do that? Anyway, so no fractions in the, yeah, there's no radicals in the denominator, and there shouldn't be any fractions inside radicals, right? They call it rationalize here. Right? Did they tell you why? No, you didn't, right? We just did it. Did you ask the teacher why? Okay, anyway, so I'm going to put the 2L inside the square root, so it becomes 4L. But I'm going to put it inside the squared too, so it becomes a 2L again. So it's R over 2L quantity squared. Are you okay with that? Okay. And then minus, when I put the 2L inside the square root, it becomes 4L squared, right? The 4's will cancel. One of the L's will cancel. So I'm going to be left with 1 over LC. Is that okay? Okay. Now, just for ease of remembering this, I will let alpha be equal to R over 2L, okay, and beta squared. The book didn't use beta. The book uses omega naught squared is equal to 1 over LC, okay. And the reason why I used omega naught squared here is I know that 1 over LC is always positive. I'm just emphasizing that it's a positive quantity. Now I can rewrite my S12 in the form negative alpha plus or minus the square root of alpha squared minus omega naught squared. Okay? Now once I know the value of S12, okay, I can use those values in order to find my solution. Remember, we started with the assumption that what? Our solution is of this general form, I of t equals e to the st. And it turns out that we can have up to 2 values of s, s1 and s2, why? Because it gave us a quadratic equation, which means that we're going to have 2 parts to the solution. One that depends on S1 and another part that depends on S2. So our general form of the solution for I of t would be A1 e to the S1t plus A2 e to the S2t. Now, the actual behavior of this function as a function of time will depend on the nature of S. Right? What do I mean by nature of S? S is the root of a quadratic equation, and from algebra we can have different cases, right? Case when both are real, case when what? They're identical, and the other one is the case when it's a complex root, right? And we will see how the behavior of I depends on those cases. So we're going to look at different cases. Case 1. Case 1 is when S1 and S2 are both real. numbers. When would that happen? When would this the quantity inside the square root sign, what do you call that quantity inside? The discriminant, okay, is bigger than 0. So that happens when alpha squared is greater than omega naught squared, right? Because quantity inside the square root should be positive. Or in terms of our variables, that happens when r over 2l squared is bigger than 1 over LC. And then you can look for the value of r that will satisfy that. What happens when that is the case? Okay, when alpha is bigger than omega naught squared, okay, the roots are real, and not only they are real, but both S1 and S2 are negative real numbers. Negative, real, and distinct. Okay, first, why am I sure that they're both negative? Well, I'm 100% sure that the one of them is negative, right? Because it's negative alpha minus the square root. That's negative for sure. How do I know that if I take the plus part, that the answer is still going to be negative?
Because alpha is just square root of alpha squared.
Okay.
And you can see that portion is going to that.
Did you get what he's trying to say? So even if I take the positive side, okay, the quantity inside the square root, the square root quantity is going to be less than alpha. Why? Because it's alpha squared to begin with, and I decreased it from alpha squared before taking the square root. Therefore, the answer in the square root can only be less than alpha. Yes? Do you understand? Did that make sense, James? Just look at me. Okay, whatever he said. Right? So out inside the square root sign, I have alpha squared, and then I decrease that before I take the square root. Therefore, the answer after I take the square root is definitely less than alpha. So even if I take positive of something less than alpha, would still, when added to the negative alpha, would still give me a negative answer. So what we know is that not only are both real, they're both negatives, right? And they're distinct, meaning they're not equal to each other. Okay? And if they're both negative, what would be the nature of your solution? So S1 is a negative real number and S2 is a negative real number. It will be the sum of two exponentially decaying functions. Right? So the solution will be what? I of t would be A1 e to the S1t plus, I'm just copying it, e to the S2t, which is S1 is less than 0, S2 is less than 0, so it's the sum of two exponential decays. That's the first case. Let's look at the second case. When S1 and S2 are complex numbers. Okay, in fact, when they're complex numbers, I know that they're actually going to be complex conjugates. Right? You understand complex conjugate, right? So complex conjugate. When does that happen? Okay, when alpha squared inside the denominator is less than omega naught squared. Okay? Because the discriminant, the quantity inside the square root sign is a negative number. When I take the square root of that, it's going to be an imaginary. So I will have minus real plus or minus imaginary number. That's going to be a complex conjugate. Okay? Now, if I rewrite my S1, S2 in this manner, S1, S2 is going to be negative alpha plus or minus the square root of, since I already know that omega naught squared is bigger than alpha squared, I'm going to rewrite the order. So I'm going to put omega naught squared first minus alpha squared. But in order not to change S1 and S2, I need a minus sign. You agree with that? I know that omega naught squared is bigger than alpha squared. So I rewrote it, that it's the same as that, right? And the reason for that is I'm going to be able to solve this as minus alpha plus or minus the square root of minus 1, right, times the square root of, okay, so let's separate them so it's clearer. Square root 1, negative 1, and the square root of omega naught squared minus alpha squared. Is that okay? Yes? Okay, and the reason why I extracted a minus 1 square root is because that's just a special number. What is that special number? It's the imaginary number, but we don't call it I. I know in algebra you call it I, but I is sacred to us, so J is what our imaginary number is. Okay? Oops. Okay? So we're going to call that J. So our solution would now be what? And I will, this is the one that I wrote on the wrong page. Okay. I'm also going to call omega naught squared minus alpha squared as some new quantity we're going to call omega d squared. Okay, so omega naught means there's no damping. We're going to understand what that means. And omega d means that it's damping. And they're both omegas because they're actually angular frequencies, as we will see, because it will turn out to be a sinusoid with a certain angular frequency. Okay, so if we do that, our S12 will become what? Negative alpha, right? Plus or minus J times, what happens to that? We call it omega D now. Okay? So it's complex, okay? Now, if you haven't taken differential equations, initially this is going to be kind of scary, because when we substitute that into our differential equation, remember our initial trial solution was of this form, right? A e to the st. It turns out that we have two s's, s1 and s2, so we need to substitute. We're going to have two constants here, a1 e to the s1t plus a2 e to the s2t, and this part may be scary because we're going to have an exponential, and the exponential happens to be a complex number. We're going to have two terms, right? S1 is negative alpha plus j omega d, and then S2 is negative alpha minus j omega d t. Are we okay? I'm just substituting the two values of S1 is the one with a plus, and S2 is the one with a minus. Okay? Now, depending on how detailed your Calc 2 teacher went into this, okay, differential equations, people should know what this is. What is e to the j theta? Well, yeah, it's called Euler's identity. It's the same Euler who has Euler's formula, Euler's method, Euler's everything. And what does it say? Oops. No, it's not. It's not pi. We have a general theta here in radians. It's going to be, it's cosine theta plus j sine theta. Okay, raise your hand if you have never seen this before. Okay. Okay, so let's start with something that I know you've seen in Calc 2, okay? So remember in Calc 2 the Maclaurin series expansion or Taylor series, okay? E to the x is what? It's 1 plus x to the 1 over 1 factorial, right? Plus x squared over 2 factorial, yes? Everyone, I mean, you've seen this, I'm sure, yes? Okay. We also have a Taylor-Swift expression for sine of x. It's x, right? So it starts with an x. The sine of a small angle in radians is the same as the angle in radians. Then a minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus and so on. Yes? And the other one, the cosine x is what? For a small angle, cosine is approximately equal to 1. And then you add minus even, right? So minus x squared over 2 factorial plus x to the 4th over 4 factorial. Everyone, I know you all have seen this. Otherwise, I'm going to send you to Calc 2. Okay. So what if I substitute here x is equal to a j theta? What happens to e to the x or e to the j theta? So it's going to be 1 plus j theta, right? Plus j theta squared over 2 factorial plus j theta cubed over 3 factorial plus j theta to the 4th over 4 factorial and so on, right? So let's simplify this. What is j squared? It's negative 1, so it becomes negative theta squared over 2 factorial, right? What is j cubed? J cubed is negative j. If that's the same as j and j squared, it's going to be negative j, right? So it's going to be negative j theta cubed over 3 factorial, okay? And what is j to the 4th? It's positive 1, so it's going to be theta to the 4th over 4 factorial. What is j to the 5th? It's the same as j to the 4th times j, so it's become positive j. So it becomes, you understand where I'm going to do this? Yes. If I collect all the ones that are real, oops. If I collect all the ones that are real, I have 1 minus theta squared over 2 factorial plus theta to the 4th over 4 factorial plus and so on, right? And then I factor out the ones with j's. I'm left with theta minus theta cube over 3 factorial plus theta 5th over 5 factorial plus and so on. And do you see what this is? So the first, all the ones here that are real is the cosine. And this becomes sine. Establishing this. Euler's identity. Okay? Okay, so give me 2 more minutes, and because we don't want to leave this function like this. Because if I ask you, what does that function graph like? You know, oh, an exponent with a complex exponent. Okay, so let's substitute that using Euler's identity. Okay, so our I of t is going to be equal to a 1. What happens to e to the negative? So it's going to be e to the negative alpha, right? E to the positive j omega t. Do you understand what I'm doing here? I'm distributing the t, right? Negative alpha and j omega dt, and I'm distributing to the e's. Yes? Okay? If I do the same thing here, plus a2, e to the negative alpha t, e to the, what's going to be on the second part? Negative j omega dt. Do you understand what I'm doing here? I'm distributing the function of time here. Okay, and e of a sum is the same as a product of the e's, right? And the reason why I did that is because I can now factor what? They both have this e to the minus alpha t, and I'm left with a1 e to the j omega t plus a2 e to the negative j omega dt. Okay, and then what do you think I'm going to do here? I'm going to invoke Euler's identity and say that What is e to the j omega t? It's cosine of omega dt plus j sine omega dt, right? What is e to the negative j omega dt? It's cosine of negative omega dt, which is the same as the cosine of the positive, because cosine is an even function. Yes. Just say yes. Okay. Yes. Okay. And then, on the other hand, sine function is an odd function. So the sine of negative omega dt is the same as negative sine of omega t. So we're going to have a negative j sine omega dt. Do you understand why both the cosines will be positive, whereas the sine, one is positive, one's negative, because cosine is odd even function and sine is odd. So what I'm going to do is I'm going to collect the like terms. So what terms would I have? The cosine omega t right? I'm going to have two terms. So one is A1, second one is A2. Yes? And then the second part is a sine omega dt, and it has two terms. Both of them have j's in front. And the first one is an A1 positive, and the second one is a negative A2. Yes? Okay? Now, it becomes less scary now because I know that the sum of A1 and A2, the sum of any two constants is just another constant, D1. Okay? Now, the difference between two constants is another constant, but J itself is also a constant. Yes? So I'm going to absorb the J and say J times A1 minus A2 is another constant, B2. Therefore, our general solution is e to the negative alpha B1 cosine omega dt plus B2 sine omega dt. Okay? So, and what is this? The sum of two sinusoids is just another sinusoid. Yes? With the same frequency, they have the same frequency, but the amplitude will be different and has phase shift. And then, what is e to the negative alpha? It's just decay. So it's really just a decaying sinusoidal function. So the graph would look like this. So here's my e to the negative alpha t. He's calling it the envelope. And then I have some sinusoid oscillating between them. So instead of having a regular sinusoid like this, the amplitude is just exponentially decaying. So it's really just an exponentially decaying sinusoid, and it looks less, what's this? Bad. Scary than having complex numbers in the exponents. Okay, I can stop now. So that's the second case. And then we also, of course, have a third case that we will look at next time. Hmm?
This is the one that breaks them off.
No. This part here, the derivation is complicated, but like before, once we solve it, you don't need to solve it. So this part of the problem is actually easy.
The part where it's pretty damn breaks the
oh yes, yes.
I had a question.
Mm-hmm.
This one, the one said fine, and it didn't say what the fine. Was it B0?
Uh,
It was B0.
it's probably B0.